This video is the discussion of the content in Chapter 19 when I use the BLB textbook, and I stick most closely to the ideas as presented in that. So in some ways, this is my most targeted, limited treatment of the content. So I list the different sections of the textbook here. If I'm teaching the class twice a week, I do Chapter 19 in about 1 week. So I'd have two different course sessions dedicated to it. So within this particular portion of it, I'm going to discuss ideas from 19.1 through 19.4. And at the bottom, I list typical learning objectives, and I like to list these in a way that it makes sense for the student, not written for a fellow teacher, but written for the student. Listing things like you're going to be involved with making rankings, doing predictions, doing calculations, language like that. The students can more easily consider how those show up as exam questions for them. So I begin by thinking about, well, what is a spontaneous process? And when we use the word spontaneous, why do we even care about it? So I start out by saying, well, these are all examples of phenomena that are involving spontaneity. Do they take place or not without the need for a continual input of energy externally? Trying to point out these are all really at the heart of chemistry. These are all things that we're interested in learning about. Pointing out that a spontaneous process is a irreversible one. This image from the textbook of what does it mean to return something back to its initial state. Spontaneous means you can't reverse it, but there's some external work involved. The reversible process, how that's an abstraction, generally considered an ideal process that occurs with infinitesimally small steps. And in this case, it can be reversed with no change in either the system or the surroundings. This bottom feature right here, this language of irreversible, reversible, infinitesimally small steps, I do very little with in my Chemistry 1220 course. In a way, I do a disservice to the students. I know that this is not something that we're going to go on and assess, so I treat it in a very cursory manner. Returning to these different processes that might be spontaneous or not, what is our criterion? How can we think about whether something is going to be spontaneous or not? I want us to think about it as the dispersal of matter and energy, the spreading out of matter and energy. If we have the spreading out of matter and energy, that's what leads to a spontaneous process. If we have an overall entropy increase. So I'm using this language of dispersal, spreading out, for entropy. I'm not using language of saying increased disorder. I'm using language of saying that we have this spreading out of matter and energy. So let's look at a few examples here involving spontaneity. So first of all, this idea that if we have a chamber on one side it's evacuated, the other side it holds gas. If we open up the stopcock, spontaneously we always have this observation. This process right here, it always seems to take place just in one direction. But what about this particular phase change? Have we ever seen H2O go from a solid to a liquid? Have we ever seen H2O go from a liquid to a solid? Absolutely. It depends on the temperature. So we're going to find that temperature may affect spontaneity. How about this reaction? Does this reaction proceed to the left or does it proceed to the right? At this point, we've been looking at ideas of equilibrium already. And it's going to depend on the concentration. Depending on the concentration, it might go from the left to the right, or different concentration from the right to the left. So concentration can affect spontaneity too. This idea of the expansion of a gas, that seems easy to predict. It always has the same observation for us. But for phase changes, chemical reactions, it seems like we need more information. We need information about the temperature. And for that chemical reaction, we need information about the amounts that were present. This idea of including concentration, that's something I add that's not in the textbook at this section, and I think it's really important. because if I want to be able to connect this to equilibrium, I have to be able to think about how the amounts are also important. So what era is entropy conceived? So I show Clausius there, physicist of the time. The time is the mid-1800s. The leading technology of the day are steam engines. So scientists and engineers, as part of the industrial revolution there, they were studying the efficiency and conversion of heat to work for steam engines like these. So consider this description. Let's say we've got a hot object that's in thermal contact with a cold object. Thermal contact, so heat could be transferred between the two of them. So what's going to happen spontaneously? Let's think about our own experience. Well, I think that hot objects will cool down and the cooler object will heat up. That's what happens every time. So how do we begin to think about that, if you want to say, in an equation? This phenomena of the hot object cooling down and the cold object warming up with the transfer of heat, Clausius' description, and this is our first description here of the entropy. So the change in entropy, delta S, is equal to the heat that's transferred divided by the temperature of the transfer. So let's look at this. Let's say we had 400 joules going from the hot object to the cold object. So the entropy change for the heat leaving the hot object has a negative sign, same kind of designation that we have for something being exothermic, and it's going into the object that's at the lower temperature. Set it up so the math here is easy for both of these. Let's add it together. Overall, the entropy change is positive. The total entropy increased as the hot object cooled down and the cold object warmed up. In a way, Clausius' description right here is simply describing this phenomena that we experience again and again. And it turns out this is quite far-reaching, but in a way, he's just given us an equation to be able to describe what was going on here. And that's the second law of thermodynamics. In any spontaneous, irreversible process, the overall entropy goes up. And when I say overall entropy, I mean the entropy of the universe. So if I combine the entropy of the system with the surroundings, that's the universe, that's going to be a positive value for a spontaneous process. It would be possible for the entropy of the system to go down as long as the entropy of the surroundings increases more. Let's look at an equation or a calculation on this. Let's say you grab an ice cube. So an ice cube, it turns out, is about 1 mole of H2O solid. Pretty cool, okay? You know, when I grab this and say, well, let me run some numbers, that's about the mass of 1 mole for an ice cube that you'd hold in your hand. So let's say the ice is at 273. We'll call that the system. We know that if we hold that in our hand, the ice cube is going to melt. The enthalpy change on that is the heat of fusion. So we have, for our system, as our ice cube, we would have the heat that was involved, the enthalpy change, for 1 mole of it, divided by the temperature that's taking place. This would be then the entropy going up for the system. The entropy is going down for the surroundings, for my hand. Within here, we have the entropy, excuse me, decreasing because it's an exothermic process. And notice the amounts here. Overall, if I'm holding that ice cube in my hand, the overall entropy is going up. Now, how do we begin to explain this? Clausius has given us an equation, a way that we can do this calculation, but how do we begin to explain it? We're going to be explaining it at the particle level in terms of probability. So let's say we go back to this chamber right here. It's evacuated on the left-hand side, 2 particles on the right-hand side. What's going to happen when I open up the stopcock in between them? Now, in order to explore this, I like this PhET sim. Okay, now this PhET sim wasn't designed for this purpose, but like many PhET sims, I take them off-road and I use them in different ways. So within this one, I'm going to raise these 2 barriers. And I'm going to put 2 particles on one side. So they're bouncing around a lot. Let me add some heat to it. Particle motion begins to increase. In some ways, this is like the old video game Pong. So what I do within this one, I have my class, all right, I want you to cheer when both of the balls are on the right-hand side. And you can lower the barrier. Let's see if that happens. Cheer, stop. Wait for it. Cheer, stop. So this one's usually pretty well received. So my point within here is, the balls don't know if they're supposed to be on the left-hand side or the right-hand side. They're just bouncing around randomly. But in terms of probability, they don't stay just on one side because they have different locations that they could be. You could have them split this way, this way, this way, this way. You've got 4 different options if you're treating those two particles as their identity, a blue one and a red one. It doesn't just stay on one side because based on simple probability, there's different spots where it could potentially be. Before opening the stopcock, they were in one location on that right-hand side. After opening it up, we find that we have more options where they can be. Only one of those arrangements put them both on the right-hand side. So simply based on probability, both of them are found on the right-hand side about a quarter of the time. Now, of course, we're usually not looking at 4 particles. We're looking at an extremely large number of particles. So how would that change the probability? Let's go back to our sim. So on this left-hand side right here, instead of having 2 particles, how about we add 50 particles? Now, we'll drop the wall. I want you to once again cheer when all of the particles are on the right-hand side. I see a randomness as they go back and forth. There is an option where they will all be on the right-hand side, but I've been watching the sim for a long time. It's never occurred for me. Far more probable is that we have a distribution spread throughout. We have a dispersal of the particles spreading out and filling up the space there. That's simply based on probability. The particles don't know that they're supposed to be distributed on both the left and the right. These are just the more probable descriptions. That idea of probability, that's the key to understanding aspects of entropy. This idea of needing a large number of particles. Do I ever see the entropy change, you could say, go down? Well, it's possible, but in the world that we inhabit, we have a large number of particles. Our atoms are so small within that typically we're in that second scenario where we see that spreading out, and that's what we observe macroscopically. That's what Boltzmann's describing. So look at this case right here. On the left-hand side, I would say we have a high pressure, and the right-hand side, no pressure. This would be like what I just set up within the sim. The macro state, that describes the different properties that we can observe, that we can measure macroscopically. I could measure a pressure on the left-hand side and the fact that there's no pressure on the right-hand side. Look at these pictures. They're not identical, but I think they produce the same macro state. The actual arrangement within them, that's called the microstate. That is the specific configuration. But typically, we have many, many, many different microstates that lead to this overall macrostate description. After we open up the chambers, we remove the barriers, we find that we end up having equal pressures on both sides. So that would be a macrostate description. Here would be another microstate that leads to that same macrostate description. The number of microstates, the number of options, the number of possibilities increased when that barrier was removed. This led to a spontaneous change, and more microstates were now being populated. This use of the term microstates, that's given with Boltzmann the symbol W. When you have more microstates being used, that means a higher entropy. This is the calculation he would be using to calculate the entropy. First of all, we typically are just going to, in this class, look at this idea conceptually. Teacher to teacher, we're not doing a lot within this class, within the 1220, of really looking at specifically what are the number of microstates and how would we do a calculation with that. I think that's something we want to know more, so when the student asks, well, what's going on there, we're equipped to answer it. So if we're looking at this then at the particle level, I'd say that the number of microstates that are possible, they increase if the volume goes up, the temperature goes up, or if we have more particles there. These are all leading to a greater option to have our matter, our energy dispersed. If you have the complexity of the molecule increase, this would also give it more ways to use the motion. And we're also going to find that the molar mass is another way, that a higher molar mass, higher entropy. So with several of these, I think these are things that we've already been looking at the particle level. If we consider what's taking place in the solid, the liquid, the gas, all of these we find with increasing entropy, we have greater and greater motion there. The motions are being described here as translations, vibrations, and rotations. Pointing out in the solid here, only vibrations are possible. In the vapor, you've got the greatest freedom of motion. Translations, vibrations, rotations, all are possible within here. We can look a little bit more closely at aspects of this motion. Energy is required to make the molecule do one of these things. Make the molecule spin around. Make the bonds vibrate. This idea that they're doing different things, that's what contributes to the heat capacity. That's another teacher idea. That's what's contributing to the heat capacity, the different ways this energy can be used. Quick aside I usually share, I like any opportunity I have for using this simulation I like to show, given the complexity of the molecule, how many different ways can it move? This was a very simple tetrahedral molecule. I see that I have 4 different vibrations possible. More complex one, more vibrations possible. Even more complex, even more vibrations possible. So the kinds of questions that we might be asked to answer within this one, here's an example. And this is from the e-text. Do we have an increase or decrease of the entropy? This is how we discuss and we'd answer each of these. The first thing I'm looking for would be, do I have more moles of gas? More moles of gas, really good indicator that's leading, that those have a higher entropy value. So I'm looking for a change in that. That's the first factor that I'm looking for. How about this one? So within this one, this is from end of chapter. And we're thinking about, well, what would be contributing to the entropy change qualitatively here? So I'm directing, we discussed this about the number of molecules changing, the complexity changing. In this case, I think we have competing factors. I see the entropy would be going up because I have more particles, but the complexity would be going down because instead of having this something with more vibrations, I've had it now with fewer. So we have competing terms within that. The one that wins, if you have more particles, that definitely dominates, leads to a greater entropy increase. How about this last feature right here, endothermic or exothermic? We can envision this as breaking the bond between those 2 blue atoms, so that would be an endothermic process. It's endothermic. In order for that to take place, we'd say that heat is going into the system. The surroundings are getting somewhat colder. This would mean the entropy change for the surroundings is going down. That's an idea we're going to use just a moment here. Now within this one, I'm definitely adding this notation to say that I'm looking at the system. Entropy we can think about in terms of the system, the surroundings, or overall in terms of the universe. So we need clarity for what we're designating there. So we do calculations where we have provided entropy value. Comes back to we can do products minus reactants. Now, important within this one, so first off, we work through a calculation. We could find for this one, entropy is decreasing for the system. This notation right here, standard molar entropies at 298 with our 0 there, we see that this is for the standard conditions. 1 molar if we have solutions, 1 atm for gases, and it's listed there for 298. Just like we need clarity, are we talking about the system or the surroundings when we're or the universe when we're thinking about the entropy? Are we thinking it under these standard conditions or other conditions that would be considered non-standard? How about this one? This is looking at the entropy change for the system under these standard conditions. So we could take the values. We could see that for the system right here, entropy is going down. This, however, is an explosion that I've done several times as a demonstration, kaboom. And so that's telling me we need to not just think about the system, we need to think about the surroundings as well. So important idea here. How do we calculate the entropy change for the surroundings? Let's think about the heat that's involved. We can measure the heat that's involved for the surroundings at the particular temperature. This would be back to our first Clausius description. By thinking in a clever way about, well, tell me about the heat that's leaving the system, because that would be the heat that's going into the surroundings. The heat that's leaving the system at a particular temperature, that is the enthalpy change for the system, if we're looking at a constant pressure. And so by knowing that it's exothermic, we can use that to calculate what was the entropy change for the surroundings. This feature right here, this is what makes the whole thing spontaneous. Thinking ahead, this is the key for understanding Gibbs free energy. Gibbs free energy is really just looking at the same idea. It's not just the entropy change for the system, it's the entropy change for the surroundings. And we can get to that by thinking about the enthalpy change that took place for the system. Another thing to keep in mind, this would be set up where we're answering the question under standard conditions. So the gases that we had present here would have been at 1 atm. Comes back to, we need to be clear, are we under standard conditions where they have these specific concentrations, or are they something else? Anything else makes it non-standard. Here's a question from the Mastering Chemistry homework system. This is a clever arrangement where they have a host of different things and you're asked to rank these. And they're set up in a way so that none of them are identical. You can do a ranking that goes throughout. When I do this in class, I usually give what the order is and then ask, what would we use to explain each of these? What explains part A? Why 1 mole of carbon disulfide at 273 and 40 liters would have a higher entropy than 1 mole of nitrogen gas at 273 and 40. What explains B? What explains C? And we work through those. The idea that within the first one here, we'd explain in terms of larger mass. We also have a more complex molecule that could lead to greater vibrations. And you can see the rationale for all of the other ones. So in this case, I give you the data and I'm asking for the explanation why. These descriptions right here in terms of things like mass, vibration, volume, more particles, higher temperature, there's different ways to represent this. There's different textbooks that show different ways that we can understand that. And BLB right now doesn't have that particular information. So as a teacher, that's another detail that I want to help you understand. Suggested problems within this, these match up with different ideas that I discussed within this video. Some are making predictions, some are performing calculations, and some are thinking just in general terms about microstates.